So I'll have, again, this lecture will be posted after class. So yesterday, as we were getting into this stuff, we didn't really get into math yet. All right, I just covered, introduction to a transformer can sometimes simply be, just kind of explaining what it is. So we went over what it is, just quick little recap. We talked about the two sides to the transformer, primary side, secondary side. Which side has the input. That's going to be where just questions are going to come from. So you connect the input voltage to the primary and you connect the output circuit to the secondary. So make sure we have those connections made. And then we got into step up and step down. All right, we talked about step up and step down. So now let's jump into a little bit more of a for usage. We're going to use these transformers and this is more along the lines of, when it comes to transformers, really, I should say, there's two ways as electricians you install transformers. Either you're installing larger transformers inside buildings for power distribution, meaning, for example, this happens a lot in industrial buildings, right? Where I'll have a large industrial building and it has a lot of machines in it. It has a lot of motors inside. So when you got a lot of motors, when you got a lot of machinery, when you have a lot of conveyor systems that are moving products, all of that equipment that's generating power works better as a whole system when we connect them to higher voltages. All right, so motors like to work off of 480, and electrical systems that power up motor, we'd like them to be 480 volts. So this is an electrical system, meaning the panel that services these motors has 480 volts in it, and then all of our motors are fed from it. But inside these buildings, you also have an office where a person needs a normal receptacle. All right, you have multiple uses for standard receptacles. So inside this building, usually in an electrical room somewhere, there's a transformer that's taking the power from the 480 volt transformer and stepping it down to a lower voltage transformer, usually 120 and 208. Now this allows you to wire up your outlets. So for my construction electricians, these are the transformers you're going to see a lot. I hooked up a lot of these. All right, and you bring in conduit to one side, conduit to the other side, and we energize these. As a maintenance person or as an industrial electrician in this building, if you are much more likely to work with these motors as a everyday thing that you're working with than have to mess with this transformer at all. This is it's almost like the main breaker on a panel. You're never going to have to touch that thing. It'll be there for 40 years. So as far as transformers go that you'll work with, it's going to be smaller ones.
So
go ahead.
If say a house has another room, right? And all the houses aren't powered on 480. But if it's 120 and they need the bottom stairs, you just make another sub panel. Yeah, you won't need the transformer.
Yes. So okay. So let's talk about residential. Residential is a little bit different. I'll draw a house to separate the two. Inside of a residential, your panel is 120 and 240. We're gonna get more into different style transformer voltages tomorrow, maybe today, because this is gonna start to bridge into three-phase a little bit. But residential voltage is that one, 120, 240. So all of your outlets inside of a residential have availability to 120 because that's what a house requires the most. The transformer's outside of the house.
Yeah.
The electrical company is bringing high voltage and stepping it down to 240. Now, if you had, let's say, for example, another house and you needed to get power to that one, then yes, you would run a conduit, PVC or whatever if you're going to go underground. Conduit doesn't matter. And here, yes, you would put a sub panel at this point. Apartment buildings, same thing. So power gets distributed like that. So in this case, Here again, when it comes to this transformer, you're never gonna ever you're never touching that transformer. That's a utility company's problem. We don't even get near that. I mean, you don't want to. There's very likely 22,000 volts on the primary side of this transformer, so that's very dangerous to even get near, unless you have the equipment and all that. So again, the transformers that you're likely going to have in your hand that you're going to need to wire up are going to be small ones. All right, so let me pull one of those up just so you guys have an image of them as far as, I'll show you the differences here since I have some images. For example, this is the large one that sits outside of the house. All right, this is three-phase though. You can see 1, 2, and 3 connection points. We haven't talked three-phase yet, but there's one of the differences. This is the one that would be inside of a building, and you can see right at the voltage numbers here, 480 volts to 120, 240 transformers. So this is very good for a building that has 480 for the motors, but then we need 120 for the outlets. All right, you can see the name right there, split phase transformer. So we're going to talk about these today. And then smaller ones yet. Let me go back one since they were on this image here. Something like this, which we have in our labs. All right, I'll pull this up from Grainger, only because it's going to have a little bit of information here as well that we can use. All right, dry type transformer, meaning there's no liquid cool or oil inside this transformer. This transformer gives you some options in the way that we can hook it up. The primary side can be connected to 480 volts or 240 volts, one of the two. Either one would be fine for the primary side. And then the secondary side, you can get 120 or you can get 240. And if I click on this enclosure here, see if I can pull it up, you can see the image there where it says primary volts 240. It says X, though it's not times, it's not 240 times 480, it's or, 240 or. So these little small transformers, you can even see it in the name, it's a general purpose transformer. These are used a lot more in lighting systems. Actually, I would say 90% of the use of these little transformers are for lighting systems. They're used all the time. But you can use it for anything that you would need a transformer for. So motor systems and control systems to step down voltages. Maybe not specifically these numbers here, right? Maybe not specifically these numbers, but these little small transformers that you see here come in different voltage applications, which we're going to get to as we start to get into the math. So you can buy any one of these. These are not on one transformer, all of those. One transformer have one at a time, right? So it'll have the ability to connect the primary side to 240 or 480 and get 12 volts or 24 on the secondary. All right, so it gives you a lot of options. 240, 480, 24, 48. It gives us a lot of options. This little transformer that they're selling here. So if you needed, this is Grainger. If you guys haven't seen Grainger yet, if you do get into industrial work, you will use Grainger a lot to order parts because they do sell a lot of this stuff. So you would just run through the transformers that you would need. Which one do I need? Do I need this one that's 240, 480, that combination, or do I need one of these other combinations? And you would just buy that one. All right, this is like, again, multi-purpose use transformers. And these are going to be a lot more of the ones that you hook up in the industrial world. For my construction electricians, you're going to see the larger ones inside industrial and commercial buildings, as I mentioned earlier. All right, so we're going to try to go ahead if you had a question there, follow up. Now, in a house, the only transformer, by the way, these days this is getting phased out. But outside, they used to have a lot of use for these little outside transformers for the lights that would be outside of the house. But now these days, all of these lights are solar. So there's another thing happening. You guys don't know this, but solar systems we won't need transformers anymore for many things. So little small transformers may even go away with solar systems. That the DC voltage coming into the solar panel, you guys are going to do a little bit of solar in this module so we can sprinkle it in along the way. The DC is going to get converted to AC, and you can set it up to to not need to do anything to the AC power that's coming off of the solar system. So for example, an industrial building can have a solar panel bank that's producing 480 and another solar panel bank that's producing 120, and maybe transformers in that sense start to get phased away a little bit. Another job replaced, not by AI this time. All right, where were we? We'll fall back. So let's try to understand these transformers in two ways. First, let's do the Ohm's law. This will be some math, but again, hopefully not too difficult, I don't think. But and then we'll talk about how to connect them for all of those different voltages. Now, one thing to mention is when we talk about transformers, we use VA as the expression of energy, or to represent power. All right, this is coming again out of the PDF that I posted. So instead of saying, like for example, if you go buy a generator, then you're going to buy a kW, watt, system generator. All right, you would buy it rated for a kW. When we're buying transformers, we're buying them to a kVA. All right, so that's the one thing on transformers that's different from other components, is they're represented in kVA or in VA. All right, now VA shows up a lot around the code book. VA is wattage. All right, that's what it means. kW and kVA mean the same thing, but not really. Here's the difference. The difference is, when you say VA, you're talking about an estimated number that you've come up with based off of a calculation. All right, so the code book and other places will use the term nominal. All right, nominal VA, meaning this isn't real wattage being consumed or used by this light bulb or this transformer, but when this transformer is in use, or when this light bulb is on, it will produce X amount of VA, we estimate. Now, when you actually plug in the light bulb to this particular lamp holder in this particular house with this house's wiring system and etc., maybe when you turn on the light bulb, you have a different actual energy usage. Maybe it's a different wattage. Right? So for example, the box on the light bulb says 15 watts. But when you actually have it on, it might be 16 watts or 14 watts or a difference of some. So wattage represents real usage of power, which is how the electrical company measures power usage in your house. They measure it off of kilowatts per hour, because watts represents actual usage of power. When you say VA, you're talking about an estimated amount of wattage that this unit will produce or need when it's operating. All right. So one is called true power and one is called apparent. All right. VA is called apparent power rating. All right. And again, wattage is sometimes referred to as true power rating. All right. So when we're dealing with a transformer, in two directions we have to deal with a transformer. One is this. All right, and it's all based off of what are we connecting on this side? All right, what are we connecting on the secondary side? Because, like with everything in the electrical world, whether you're wiring something up or whether you're selecting a breaker for the thing that you just wired up, it is all based on how much energy does that thing produce while it's in operation. So, small little transformer, let's say, for example, using yesterday's example, that's going to be used for a doorbell system. Well, the doorbell doesn't produce a lot of wattage. It doesn't produce a lot of amperage. All right, so this is a small little transformer versus the transformer that's feeding the house, where the load side here is your entire house. All right, so the size of the transformer is going to, again, be based off of the load it's connected to. This is on video. It's not going to come up in a test question, but if you wanted to write that down and, you know, something you really wanted to learn about the transformer, that would be something to write down. All right, they're selected. When you go to buy a transformer, you are, what am I wiring up? How big is that? And again, the idea is to eventually figure out how many kVA, or, you know, it could also be just VA if we didn't get over the thousands. But, you know, a lot of times these transformers do get a little bit bigger than, so either one, right? So that's what we're trying to figure out, right? It's different from a breaker. For example, for those of you who've talked more about breakers, when you go to select a breaker, you're not selecting a breaker based off of what you are wiring up's wattage or VA. You are selecting the breaker based off of what you're wiring up's amperage. Right? So a breaker is rated for, let's say for example, 20 amps, not wattage. Whereas a transformer is based off of the wattage of what it's going to be powering up. Now, by the way, could it have been based off of the amperage? Yes. They would just have to have done ohms. We're going to do it, so we're going to figure it out. But just so you understand, when you go to buy a transformer, you're buying it off of the wattage that is going to be energized by this transformer. Okay, so this is the only thing we need to really know about a transformer is, comes down to this, the turn ratio of the transformer. All right, that's the most important thing that we want to know about the transformer is the turn ratio. So first of all, what is the turn ratio? It has to do with how many turns on the windings does one side have versus the other side. Now, this one is representing a step down transformer, remember, and I'll just go back to those notes to remind you of where I got that from. Excuse me. Oh, actually, I may have, I erased that part, but if it would have been a step up transformer, then X1 and X2 would have been on this side with H1, actually, H2 there, H1 on the bottom. All right, so you may see it the other way around, but we'll get to that later. Let's just understand this part. So they're going to be different from each other. That's how we get the change in voltage. Whether one side has more than the other, whether it's a step up or a step down, doesn't matter. All we want to know is what's the difference between the two. Now, there's a few ways that we can get to this number. One would be very easy, which is the manufacturer of the transformer told me how many times they turned the windings. They can just tell me, okay, this side we turned it 2,000 times, and this side we only turned it 500 times. So now I can come up with this turn ratio calculation. But a lot of times they don't tell us that. All right, they're not going to tell us that. What we are going to know about the transformer is the voltage part of this transformer. What is the primary side's voltage coming into the transformer? Let's just say doorbell transformer, just for example right now, 120 coming in and 12 volts coming out of the other side. This is the information that we get from the transformer. All right, the incoming voltage and the outgoing voltage. So now from here, again, if you told me the 2,500, that would be good, but they don't tell us the amount of times they turned it. Sometimes they do, sometimes it's on the box, but it's so not necessary that they don't even take the time to put that in for us. So here's how we get to the turn ratio. Again, for the in-person students who've already walked through this a little bit in their labs, online, this will be the first time hearing it. We just take whichever the larger number is of the two. All right, for example, if this was a step-up transformer, then it would be 12 on this side and 120 on this side. But the math is done the same. Bigger number of the two goes on top. Smaller number of the two goes below, and now we divide.
10?
Correct. Now, here's the important part. When we're writing it down and expressing it, it's 10 to 1. All right, it's always going to be to 1. So this is a 10 to 1 transformer. And we can do that for any voltage. And again, no matter which side is the primary or the secondary, that part doesn't matter. There is only one minor thing that would matter if this was 12 volts here and 120 volts here, meaning step-up transformer. We'd do the math the same. We'd come up with 10 the same, except when we express it, we would put exactly 1 to 10, correct. It just flips. The bigger number follows the larger voltage, really. That's an easy way to remember it, right? On this one, it's 10 to, but on that one, the larger number was here. Few ways to remember it, or just remember it. So we'll just work with the other one. It did not matter which one we did. 10 was the outcome, so there's where we got 10 from for 10 to 1. Now, 10 to 1 tells us a lot of things. First of all, it's letting me know that the turn ratio and the voltage ratio are the same. All right, so we can write that as a note. I'll take a fresh page here to write that, which is voltage ratio. This is a good note to have. Is equal to turn ratio. I'll just write TR. You can write that out. But here's the other part we know. We're going to write another note to this one as well. Here's the other thing, that is that the current ratio is also the same or equal to the turn ratio as well. Which would then mean, although you don't have to write this one down, so I'm going to put it in another color. It is the result of this, which is voltage ratio and current ratio are equal. Current ratio, right? Because they're all equal to each other, which is what this is letting us know. So again, now once I know that the turn ratio is 10 to 1, then I know that the current between the primary and the secondary side is also 10 to 1 as well. If the current was 10 amps on one side, then it's 1 on the other. All right, we'll get to how we can figure all of that out, but that's the first part to it. So either I know the 2 amperages of both sides, I can come up with the turn ratio. I know the 2 voltages on both sides, and I can come up with the turn ratio. Now, here's the last part to this, which is watts stay the same. So the VA stays the same. Oops, let me clean that up. On both sides. All right, on both sides. So on the primary side, the wattage is the same as the secondary side. All right, so wattage stays the same. Voltage ratio is equal to the turn ratio. Current ratio is equal to the turn ratio. And again, the last one is a fact, but we don't need it for what we're going to do over here. All right, if anybody needs me to go back for those notes, let me know. If not, let's work out some math. Now, because I know the size of the transformer on the VA side, remember, that's how I bought this thing, then I'll have that information as well. So I'll know if this is a 5 VA transformer, or a transformer that is only going to handle 5 watts. That's very small. So we can give this transformer a little bit of wattage capacity. So let's say it's going to handle, let's say 50 VA. All right, so when we bought the transformer, that means wattage is the same on both sides. Now, this is important to understand, and I tell this to students in the code classes when they're learning about voltage being distributed to outlets, and they talk about amperage and all that. It doesn't mean to say that the transformer has 50 watts inside to give to whatever gets plugged to the transformer or connected to the transformer. All right, the transformer is not giving anyone 50 watts or 50 VA. The transformer is able to handle up to 50 watts connected to it. If you connect something to this transformer that produces 100 watts when you turn it on, you're going to fry this transformer. All right, it'll just get heat up too much and it'll break. So it can handle, if you needed a one, that's why I say you buy the transformer based off of the wattage demand. So if, for example, we're hooking up a bunch of LED lights outside of a building, wherever, doesn't matter, and each one of the LED lights are 5 watts each, then we can put 10 on this particular small transformer. All right, say for example the LED lights were 12 volts with 5 watts each. All right, using the voltage we have here for this transformer. So we can get 10 of these lights on there. So now we have 2 bits of information to do Ohm's law. We know the primary side voltage. We know the secondary side voltage. And now we can get to the amperage. Now you can do this in one of 2 ways, but, well, no, actually with this one is only one way. To find the first number here, because you don't have any amperage yet. So you can divide either side to get to a number. Either one will be fine. Let's do the secondary side. So we'll divide 50 by 12. All right, that's the Ohm's law, P over E, power over voltage, equals I. All right, that's very useful Ohm's law because I is always what we're looking for. We're always looking for amperage. If we're going to buy a breaker, we need to know amperage. We're looking for wires, we need to know amperage. So this is a very useful form. Now, if I do that, I calculate that out. It comes out to 4.16 amps. And now you can do this one of 2 ways. Either you can do Ohm's law again to figure out this amperage, or you can divide this by the turn ratio, because this current is going to be 10 to 1 of the 4.16. But let's not do it that way first. Let's do just straight Ohm's law. In other words, let's take 50 and divide it over 120. And now if you look at your calculator, you'll notice the number is point, and then same thing over here, 416. Right? It's 10 to 1 of that. But the reason why I wanted to do it like that first, just using this formula, is because you have to remember what happens to the amperage and what happens to the voltage on the different transformers. All right, so this is a step-up transformer, step-down transformer. All right, means the voltage on this side is higher, the voltage on this side is lower. So for you to know what the amperage is going to be, you have to know that the amperage now on this side is going to be smaller than the amperage on this side. All right, you're going to have larger amperage on the secondary side. So that could be a setup to a question, right? In a step-down transformer, which side has the higher amperage, the secondary side or the primary side? And then everything switches up if this was a step-up transformer. All right, everything just goes in reverse. Remember, wattage always stays the same. All right, so let's try one more. All right, let's set this up another way. All right, and now I'll set it up in a way now that you're going to deal with it as a question. All right, so for the example, the question could, only give you a couple of these things and ask you for one of the other ones. So, for example, it can say something like this. We have a 5-to-1 turn ratio transformer. So you have the turn ratio. All right. You have a secondary side. All right, you have a secondary side wattage of 1200 watts, or VA. And you have a, for example, say something like, let's say 24 volt on the secondary side. So the question could ask you something like this. All right. What is the voltage on the primary? All right, so all it's looking for out of all three of these here is the question would just be looking for one of them. It's not going to look for, well, it could look for power, just to remind you of power being the same on both sides. But in this case, it's just asking us for what the voltage is on the primary side.
Do you divide 24 volts by 5?
Right, so now that's the question we have to ask ourselves. Because this is a step down, what is the voltage going to look like on the primary side? Is it going to be bigger or is it going to be smaller?
The primary one is bigger.
Bigger, right? So when we're going up, in this case, we would multiply exactly by 5, which would then equal the voltage on this side.
So 10 and 50 and 120?
Is it 120?
Yeah, 120 volts, current 10, primary 1,200. I mean power.
Yes, power 1200 on this side as well. And so now for the current on the other side, you don't have to do Ohm's law now because you're going, which way is the amperage going to be on this side? Is it going to be bigger on this side?
5 times 10?
Exactly. Now because we're going up in this one, it would be 5, and that is 50 on this side. Very good. So you could always do Ohm's law. Or you can use the fact that you have a knowledge of the turn ratio to do like we did. Multiply this one to get that number, and multiply that one to get this number. But at the end of the day, we could have just done Ohm's law to get here, and we could have done Ohm's law to get here. Either one would have gotten us 2. Now, why no one versus the other? Because of just speed to get to the answer on some of these. I'm not gonna, our exams are timed, but not like in a crazy fashion. So.
Why system?
Right. So in a single phase, this isn't Y or delta. Single phase, that's only when we start to set up the transformers in 3-phase. Y and delta are 2 different connections of transformers. A Y transformer is connected in parallel, and a delta transformer is connected in series. So we'll get to 3-phase tomorrow, but 3-phase transformers are 3 single-phase transformers connected in either series or parallel for one or the other.
Cool.
All right. So I think that's good. I don't think I have anything else that I wanted to. We'll do a few more examples as we go into the well, as we get into doing other examples, because I want to show you guys how to connect these. And then when you connect these, you're also going to be doing turn ratios and coming up with these. So we'll do more examples of the Ohm's law. But again, it boils down to also, it gives you just, if you can understand these 2 points that we made here for the step down and the notes that we had yesterday as well for the step up, That step-up transformer has the same. So it helps you learn how to use the turn ratio to your advantage to understand the voltage versus the amperage as well. And again, knowing that they're equal to each other gives us that ability. So now here's the other important part of the transformer. One is, again, when you go to order this transformer, you're going to connect it to the load. So you're worried about the load's wattage, because that's how you're going to buy the transformer. So for example, this transformer would be a 1.2 kVA transformer. I mean, you don't have to buy it so close. You can certainly buy a 1.5 kVA transformer, and that would be fine, as long as you're over 1.2. I don't know how they sell these transformers. Maybe that you can only find a 5-watt transformer. So, however it is that we go to buy this at that point. Or 5,000, I meant to say, watt transformer. So, it just can't be smaller than the 1200 that you need. All right, now we're going to get into the connections of these transformers. All right, when I popped open the Granger one, and see if I can go to it. No, of course. There we go. When I pulled up that Granger one, you saw this name where it said split phase transformers. So let me kind of talk about that for a minute. There's a few types of small transformers that we use out there, all right, out in the field. Let me give myself a page here. So one of the transformers that we buy are transformers that have single input, single output. Like the one I keep mentioning over and over, just for now, it's just what's in my head, but the doorbell one. The doorbell one is 1 voltage in and 1 voltage out. There, I mean, not just doorbells, you can use this anytime you need 12 volts. But you can only connect this transformer to 120 volts on the primary side, as we said yesterday, hot and neutral. And then you would only get 12 volts on the secondary side. This is one type of transformer that they sell. There's another type of transformer out there that they sell that's a multi-tap TAP transformer. And the connections there, it's in the PDF, so I'll go to it just to show it. It'll give you a lot of options on the primary side with a common, right? So if you're connecting to 120, then you would use the white and the black for the neutral. If you were connecting any of the other voltages, then it would be hot and hot to the common. That's why they don't say neutral. The black wire says common. So it would just be the other wire, meaning not just 120 on this side. You can connect to all of those different voltages. These are great for repair. You carry these on the van for service, and you walk into a building, you're like, what voltage is going to these lights? Oh, 277. Great. This one could be connected to 277. What voltage is connected to those lights? 120. Great. I can use this one for... So it just any voltage that the lights are connected to or that the building has. Now, on the secondary side, this one only gives me 24 volts on the secondary side. But they have ones that are the same as the primary side on the secondary side, where I get multiple outputs as well. All right, so they have those also. But the split phase transformers are a little bit different. All right, actually, let me pop that back up. These transformers and those transformers here, they have one solid winding. All right, those are one solid windings. I'll illustrate what I mean here. Even though it's multi-tap as far as many voltages can connect to it, it's just one long winding where common is on the outside. And if you connect to here, then this area is the 120. If you use more of the windings, you connect to the higher voltage, 208. As you start to use more of the windings, more of the voltage, and so on and so on. I don't think I have enough room for 277 and 480, but you get the point. if I'm going to connect this primary side to 480, then I need the use of the full winding because it's the highest voltage. And one of the things that our windings have to have is long distances between the point A and point B when the voltages get very high. So it's just one winding that you can multi-tap into it. So transformers are built in two ways. Again, there's different voltages that can connect to the primary, different voltages that can connect to the secondary, etc., but they're only built in two ways. Either the windings are like this, one solid winding, or the windings are split in half. And this is called a split phase winding. And what this does is something very, very, very interesting. It translates to your labs, and it boils down to the principle of what we're trying to understand about transformers. All right? Because we're going to be able to connect these 2 points together. All right? These two separate windings, because this is now a separate winding from that one. We're going to be able to connect them together in 2 different ways. There's only 2 ways that we can connect anything in the electrical world, and that is in series or in parallel. There's no other way. So we're going to be able to connect these in series or in parallel, and I'll show you how we do that, on both the primary side and on the split phase side to the secondary winding as well. And what ultimately this is going to result in is in us using the turn ratio of the transformer to our advantage. All right, because as we connect the primary side in parallel and in series, we're actually choosing between the different turn ratios that these transformers have available. All right, so let's boil that down and get a better understanding of it. All right, so as I mentioned when I showed you the transformer earlier on, I showed the image of the transformer. The transformer is one of the type of transformers that you can select to have different voltages connected on the primary and get different voltages on the secondary side. All right, so let's come over here where I have these voltages. So after you selected your transformer based off of the wattage that you needed to cover, remember that's the first thing that we select the transformer based off of. The next thing you have to do is application on voltage side, because ultimately what I'm going to use this transformer for is the change of voltage that it's going to give me. So these are 4 different transformers that I can order in the world of split phase. And by the way, these aren't the only ones. There's a bunch of other different voltage combinations. These are the ones that we're just using as our examples. There's 36 volts 2 out there and a couple of other combinations. There aren't thousands of them, but there's like another 2 or 3 more. Maybe 4. So I have to now know 2 things about what I'm working with. I got to know what voltage do I have available nearby, because that will mean which primary side do I have to buy. And I need to know what voltage do I need on the secondary side, because that will dictate which one of these combinations that I need to buy. All right, so any one of these can function. Again, it's now application of, and so our examples are going to come with different ones to work with. So that's the first part to this. All right, whichever transformer we're talking about, it means that we're going to connect the primary side in either 240 or 480 or 120, 240. The other ones are 240, 480, so we don't have to do those. And then on the secondary side, the only 2 voltages that I can get are either 12 volts or 24 volts, but we'll talk about that. In this combination, I would get 24 volts on the secondary side or 48. And in this combination, I would get 120 or I would get 240. All right, so that's what that's telling us. Again, the X is not multiplied by, it means or. So it's always first connect the primary, then connect the secondary. I don't mean that in order, but first it's what do I have on the primary side, then what do I need on the secondary? Because I have to first match what's in the building that I'm working in. All right, so we can pick any one of these transformers. Let's say we're going to use this one. All right, but again, it doesn't matter which one we're using. Now, here's the first part of the connections. All right, the first part of the connections is we have to connect these points to each other, all right, in two different combinations. But it depends on which voltages we're choosing as to whether or not this is going to be parallel or series. So here's an easy way to understand this. I'm going to divide these in half. And if we are, for example, connecting the primary side to 240 volts, because that's the voltage that's available nearby, we got 240. And yeah, exactly, on the secondary, I know in person you guys have gotten this, but online is not, so let me just run it through that. Very good. We are on parallel sides. If I want to get the secondary 12, then we're going to hook up our transformer in parallel. So the easy way that I like to write that is anytime we're connecting on the primary side to the smaller voltage of the two, then we're connecting the transformer in parallel. Anytime we're using these voltages on this side for our connections, then we connect the transformer in series. Both sides the same. But what does that actually mean? It means as it comes to the connections, here I'll write them. When we're connecting in parallel, we connect H1 to, I'll put it like, well, I guess I'll do it this way, because we already, to H3. And the same goes for X as well, right? So we can just say it like this. When we're connecting in parallel, we're connecting the 1 to the 3, and we're connecting the 2 to the 4. Now, how this is done is with jumpers or with jumper wires. Either one is fine. On the terminal point, you would land one end of your wire, put a little jumper, and terminate it to 3, 1 to 3. And then same thing, little jumper. They sell these jumpers, and also we make them with our wires. For my online students, I'm going to set this up with video as well, and images. Really, it's what it's going to be. I don't think it's going to be video for this. We don't need it so much, but that's what we'd be doing. Stripping out, that's why you guys got wire stripping out, and jumping between the two. Now, if we were connecting them in, remember, this is the same for both sides. I'm just not drawing it because I'm writing there, but this side would be 1 to 3 over here, and a jumper 2 to 4. So I'm just using the top as the example, but we would do it on both sides. I'm going to erase so we can do series. Series is a little bit less involved because series just connects the 2 and the 3. So we would put a jumper from the 2 over to the 3, and that's it.
And then the hot and the neutral would be on the H1 and H4?
Exactly. We always bring our wires in on the 1 and the 4, and outgoing on the 4 and the 1 as well. Incoming power to 1 and 4, outgoing to X and 1. Now, here's the other part that I want you to know, and that's why. Why do we connect it this way?
I'm sorry, you said for the X, the input would be the X4 and the output would be the X1?
Yes,
Okay.
correct. And then if,
Okay.
yeah, and we'll do a couple of examples. I have a couple of these, and we'll do individual ones. All right, we'll do a couple of examples now. All right, so now that we got it, or at least we have the notes, now let's start to piece this together individually. All right, so say we're working with this transformer, right? The one we're working with is 120 or 240 on the primary side. And on the secondary side, I can get 12 or I can get 24. I can't get both, and I cannot connect both voltages to the primary. It's either one or the other. All right, plugging it into an outlet that's 120 or connecting it to something that's 240. Either one is fine, so whatever's available is good if these are the two that I have. So technically, we can go 240 and get 12 volts. Or if I don't have 240 nearby and I have 120, I can get 12 as well. Or I can get 24 or 240 and 24. You guys get the point. So this is both ways that this question can come at us. Because when you are selecting between the parallel and the series connection, all right, so let's make a quick selection. Let's say we have 120 volts nearby, so we're going to connect to that. And I'm going to connect this to some lights that are 24 volts. So I need to connect my output so that I get 24 volts on the output. So for my primary side, we don't have to put that. We know the H's mean primary. I'm going to connect it in parallel, meaning my 1 connects to the 3.
2 to the 4.
Very good.
And then the bottom gate series.
Exactly. So now the other question we're going to ask you here is
Feels fine.
5 to 1. Very good. What's the turn ratio?
5 to 1.
Exactly. And now we would 5 to 1. Or actually, it shouldn't be written like that. Sorry about that. Let's write it correct. 5 to 1 turn ratio. And that's really what you're building. All right, this is important that you understand this part because this is the part that sometimes lands confusing. When you set up this transformer with parallel on the primary and series on the secondary, you're not really setting up a transformer that has to receive 120 and is going to produce 24 volts. What you're setting up is a transformer that's going to convert whatever voltage you put on the primary side to 5 to 1 of it. All right, that's the important part to take away as well from this because it translates also to how you're going to receive some questions and for labs as well.
If it was 240 to 42, obviously it wouldn't be fine.
Say it's 120 volts though, the only limitation is you can't exceed 120, right?
Exactly. Technically for this transformer, you can exceed 240.
But if like we select the 120 to 24 configuration, then it would be limited to 120.
Then yes, correct. Now you're limited to 120, yes.
Right.
So that means that I can connect to H1 and H4 60 volts, and I'm going to get 5 to 1 off of that. So the secondary side voltage, I should expect 12. I should expect 12 volts on this side. No 120, no 24. I connected 60. I'll get 12 on the other side. Because again, when you set up a transformer in series or parallel, technically what you're setting it up is to the turn ratio that you are setting it up to, not to the voltage specifically. So 24 and 240 is now our 10 to 1, and that would give me a 10 to 1 result of this 60. So I would get 6 volts here. If I connected this transformer at, let's see, I'm running out of colors, but 240 and 12, then I think that's 20 to 1, off the top of my head, I believe.
How would we make that a step up?
So using 3 volts.
Bring the voltage bigger on the other side. Yeah, step-up transformers are really just inverted step-down transformers.
Okay.
So any transformer that's step-up, if you connect it incorrectly, can be a step-down or... sorry, every step-down transformer, normally that's what we're working with. If you connect it incorrectly, will be a step-up.
And instead of dividing, we would multiply the turn ratio, right?
Correct. But I will tell you, I've never hooked up a step-up transformer. I've not worked with them. They're not as common in the world of power and electrical distribution. It's almost always we're going in the downward direction than in the upward direction. But these days, they do show up. They show up in like for my folks that did earlier code classes. There's this thing that happens when you run wires very long distance. It's called voltage drop. And the further away you are from the panel to the load, like if you're running 1,000 feet of conduit and wire, that's going to have a lot of drop in voltage. So you might start off with 240, but by the time you're measuring the voltage 1,000 feet away, you're going to have much less. So one of the ways you can compensate for that is a step-up transformer somewhere along a long distance run. Now, it's not as common for us to run into a situation like that. For example, the power company runs into that a lot as they run power lines very far. So they use a lot of step-up transformers, but we just simply don't have a lot of uses for them. All right, so let's approach this question now like that. Let's say we're connecting this transformer, let's say in series on the primary and in parallel on the secondary. And now let's say the incoming voltage or input voltage, whoops, there's a way to write it, I'll just write it all out. Input voltage is, let's say we're connecting 100 volts. And so what we want to know is what the output voltage is.
Fine.
Is it? Yeah, maybe. I don't know. Great. That was quick. 480 divided by. Yep. Good. So again, not too common. Not many turn ratios. Not 100 turn ratios. Only 3 of them they can be here. So yes, the first thing we want to do is take 480 and divide it by 24 equals 20. I'll put it over here. Running out of room. That means it's a 20 to 1, and now you divide that by 20. And so 5, right?
Yes.
Excellent. All right. I think
We're done?
yeah, I think we're good. Then we get into 3-phase. All right, we're paused. We're good. We're all set up. Tomorrow I'll mention it, but I'll post a couple of an assignment that goes with this one. All right, online, if you guys got those notes for today, then we'll start to translate for your labs. These connections that we just did today are how we're gonna start to set up our labs with series and parallel. Keep these notes. I'm gonna still structure your labs. I know again a few of you did not, or one of you didn't have your trainers yet, so no rush yet. I'll have this stuff for you guys probably posted tomorrow, or may even wait till Monday for it. If you guys have any questions, feel free to hang on. If not, you guys are all good to go as well. I'll see you guys tomorrow.
See you tomorrow.